Hello everyone, welcome to this video on BGP fundamentals, part 1. Firstly, I really apologize for the delay in getting this video out. Apologies, this has been about 3 weeks delayed, so I really apologize there. But nevertheless, we're here in this first part and really excited for this lesson. So let's get into the lesson breakdown. So this lesson is going to have 7 parts to it. So we're going to first be looking at ACE numbers, ASNs. Then we'll be discussing BGP loop prevention, path attributes, address families, eBGP and iBGP, BGP messages, and finally BGP neighbor states. So, but let's firstly just look at 3 key terms I want to talk about. So, firstly, what is a prefix and a prefix length in BGP? The prefix is the reachable destination. The prefix length represents the number of bits set in the subnet mask, and the network layer reachability information, LLRI, is the prefix length and the prefix. So I just wanted to go over those terms there. Now, let's talk about AS numbers. So AS numbers. Firstly, let's talk about an autonomous system. What is an autonomous system? It's a collection of routers. That's under a single organization's control. It's basically like an administrative domain in BGP. It's a collection of routers under a single organization's control. For example, you have organization, let's say Starbucks, or in the UK we have Costa Coffee, which is a British coffee chain. Now that a British coffee shop chain. Now Costa or Starbucks, they will probably own an autonomous system, or maybe even multiple autonomous systems. But for example, Starbucks is global, as well as a worldwide coffee chain. So they could have many autonomous systems, for different countries that they're in. For example, if they're in Hong Kong, they'll have an autonomous system, and for Hong Kong, and for the United States, they might have several in the United States, and in France, they might have their own autonomous systems. But basically, it's a collection of rules that's under a single organization's control. So an autonomous system is using one or more IGPs and common metrics to route packets within the AS. So like I said, organizations own these autonomous systems. They're under the control of organizations. It's a collection of routers under a single organization's control. And one organization might have one AS, but another organization might have several. It depends on the how large those networks are. So if multiple IGPs or metrics are used within an autonomous system, the autonomous system must appear consistent to external ASs in routing policy. So if multiple IGPs or metrics are used within an AS, so you can have OSPF and EOGRP running within an AS. Now the AS must appear consistent. That AS must appear consistent to external ASs in routing policy. There needs to be consistency between them. Now, however, an IGBGP is not required within an autonomous system. So an AS autonomous system could use BGP as the only routing protocol. So so you could use iBGP within, and that can be enough. You have external BGP, eBGP, and iBGP as internal BGP. You could just use iBGP within the AS, and that would be enough. It doesn't need to have any other router protocol. It can, but it doesn't have to. So I just want to emphasize that multiple IGPs or metrics are used within an AS. The ASs must appear consistent in the external ASs and routing policy. Let's look at AS numbers now. So if you've seen my channel videos recently, you might have noticed, you may have seen this video, which was about AS and AS numbers. Now, ASNs. Now, originally, there were 2 bytes. Remember, one byte is 8 bits. 2 bytes is 16 bits. So ASNs were originally 2 bytes. Making 65,535 ASNs possible. Now RFC 1493 expanded this field to accommodate 4 bytes, 32 bits. So that made circa 4.2 or 4.3 to round it up correctly, 4.3 billion unique ASNs. Okay, so 4,294,967,295 unique ASNs possible. Okay, so circa 4.3 billion ASNs we get from 16 byte from 16 sorry from a 4 byte field. Okay, 32-bit range. Okay, so we get 2 blocks of private ASNs. Okay, so 64,512 to 64,534, that's for the 16-bit range, and 4.2 billion to 4.2 so 4,294,967,294 is the private ASN range for the 32-bit range. Let's look at BGP loop prevention now. So we've just looked at ASNs, BGP loop prevention. Now, in BGP, we've got something called an AS path attribute. Okay, it's a well-known mandatory attribute, and I'm going to discuss these terms, what these mean. But the AS path attribute includes a complete list of all ASNs that the prefix has traversed from its source. Okay, so all the autonomous system numbers. Okay, for example, 65,500, 65,001, 65,002, 65,003, separate ASNs. Okay, and now the AS path attribute will include a complete list. Now, the AS path is used as a loop prevention mechanism. Why? Because BGP can get pretty freaked out, and what I mean by that is if it were to receive a prefix advertisement, okay, with its own AS listed in that AS path attribute, that would freak it out, and it would discard that. Okay, it would discard the it would discard that because it would discard the prefix because the router will perceive the advertisement to be forming a loop. Because if he sees his own number, ASN number, in that you can see, okay, for example, you got router, it's got an ASN of 65,001. It receives a prefix advertisement saying that has its own 65,001 ASN in there. That's going to look like, and that is going to read that as, oh, wait, hang on a second, this prefix advertisement has already got through me and it's come back to me, and if I send this out again, it's going to come back to me and we're going to get a loop, and we don't want loops, okay, because they circulate, and they that will ruin the internet. Okay, we can't have these loops, so rightly so they will drop those prefix advertisements. Okay, I'll drop that prefix out because okay, it will see that as something that's going to form a loop. Okay, and that keeps the internet stable, prevents prefix from circulating indefinitely between ASs and generating those loops. Okay, so sorry, this was for the last slide, but this was, I've covered this. Okay, now this is something important to know. ASN's 65,534 and the 4,294,967,295. These should never ever be used. Okay, these are the last ones in those private ranges. These 65,534, not 5, sorry, 65,534, 535, and the last that should be 5 there, sorry, 535, and this number here, that's correct. These should not be used. Okay, those should not be should not be used. Okay, and that's defined in RC 7300. Okay, now path attributes. Now path attributes, they're associated with each network path. Now the PA's path attributes provide BGP with granularity of routing policies within BGP. Granularity of routing policies. Okay, so that's what they provide for us. Granularity of routing policies within BGP. Now there are 4 prefix PAs are classified as below. Okay, that we need to know about: well-known mandatory, well-known discretionary, optional transitive, and optional non-transitive. Okay, well-known mandatory, well-known discretionary, well-known, sorry, optional transitive, optional non-transitive. 4 path attributes. Okay, so what's this all about? Okay, like I said, granularity, and you get control of routing policies from path attributes. Okay, that's what they're providing for us. Now you got these 4 well-known attributes. Firstly, these must be well. What does that mean? Well-known means that this provides a consistent understanding of behavior across all types of BGP routers. Okay, you get a consistent understanding of behavior. Okay, this attribute means has a consistent understanding between all the vendors, and the different versions that you have of BGP. This is understood across. Okay, so those types of attributes that are called well known are across the board, regardless of the vendor. Cisco, Juniper, Palo Alto, Aruba, they're all understood regardless of the version. Okay, so mandatory just means that the attribute needs to be in every BGP update sent. Otherwise, that's going to be regarded as corrupt and discarded. Okay, it has to be in every BGP update. Okay, now examples are next top. So origin and AS path. Okay, so well-known mandatory attributes must be included with every prefix advertisement. So an example is if a BGP update is sent and that prefix does include an AS path. Because an AS path is an example of well-known attribute, that BGP update is going to be dropped. Okay, so if you got, this is important to know for troubleshooting. Okay, if a BGP update is sent and that prefix doesn't include an AS path, that BGP update is going to be dropped. Okay, very important to know there. And if we keep going, well-known discretionary attributes, these may or may not be included with a prefix advertisement. Okay, so discretionary means that this attribute is not required to be appearing in every BGP update. Okay, so well-known is the same definition here, is across the board, regardless of vendor or version. But discretionary means that the attribute is not required to be appearing in every single BGP update. It doesn't need to be in every single BGP update. These attributes are recognized by all routers, passed by all pairs, and option included in the update message. Okay, optionally included. It does not require to be appearing in every BGP update. Is a case recognized and understood across the board, but passed to all pairs, but is optionally included in the update. It doesn't have to appear. Now, the well-known discretionary attributes include local preference, local pref, and atomic atomic aggregate. These are 2 types of well-known discretionary attributes. Moving on to optional attributes. Okay, you got optional, transitive, optional, non-transitive. Okay, now optional attributes do not have to be recognized by all BGP implementations. Okay, optional attributes, they can be set so that they are transitive and stay with the route advertisement from the AS to the S. Okay, but other path attributes are non-transitive. So the non-transitive optional attributes, they can't be shared from AS to AS. So if you look at optional transitive path attributes in more detail, optional means the attributes not required to be recognized by all BGP implementations. Transitive just means that the attribute should be passed on to other BGP peers. For example, optional transitive path attributes are possibly recognized by BGP routers and passed to BGP peers. Examples include aggregators and BGP communities. Non-transitive, like I said, optional, it means it's not required to be recognized by all BGP implementations. Non-transitive means if the attribute isn't recognized, the attribute won't be passed on, but rather discarded. So multi-exit discriminator, MED. This attribute is an example, and this suggests the preferred path to external neighbors when multiple paths exist to reach that destination. Okay, so the multi-exit discriminator is basically a way for preferring choosing a preferred path in a manner that's not going to affect other autonomous systems, okay? It suggests the preferred path to external neighbors when you have multiple paths existing to reach that destination, the same destination. So the ACE path attribute, just to talk about ACE path attribute a bit more, it's a well-known mandatory attribute. It includes a complete list of the ASNs that the prefix advertisement has traversed right from the source AS. Okay, so example, if you can see, you've got, apologize, sorry, let me go back into the presentation. So if I just go back to, so here you've got, so you got loop prevention mechanism in BGP. So I was talking about loop prevention. This is a prefix advertisement. It sees this AS10 here, sees its own AS number, ASN in the prefix advertisement. That's why it freaks on, it drops that. Okay, it drops the advertisement there. Okay, it discards that prefix. Okay, so it drops the prefix, should I say, sorry. It drops the prefix. Now we know a little bit about the AS path attributes. Let's talk about, okay, we talked about AS path attributes. Let's talk about address families. So BGP was originally intended for routing of IPv4 prefixes between organizations, but RFC 2858 did something quite revolutionary. It added something called multiple protocol BGP, and now this made BGP more awesome, the way I like to think of it. Okay, it was revolutionary in a way because by the way, we had something called the address family identifier that was created in that, okay, the AFI. But multi-protocol BGP made BGP's abilities a lot more, okay, enhanced its abilities because it supported IPv6, VPN, unicast, and multicast, okay. So multiple network layer protocols were supported, okay, using the concept of address families. An address family correlates to specific network protocols such as IPv4, IPv6, and you get additional granularity through subsequent address family identified, the SAFI, okay, the SAFI. So the question to you is, do you know how address families maintain databases? My question to you, do you know? Well, what happens is, you have address families, they maintain databases by having a separate database and configuration for each protocol. Okay, so we have separate database and configuration for each protocol. Okay, so because we're dealing with IPv4, IPv6, we're dealing with VPN protocol. Okay, so we've got a separate database and configuration for each protocol. Okay, so you got an address family and a sub address family in BGP. Now, okay, so you get this allows for this allows for routing policy in one address family to be different from the routing policy in a different address family, IPv4, IPv6. All the while, that router is going to use the same BGP session with all the router. Okay, so you got different routing policy for different address families. But what the cool thing is, you still got the same BGP session, guys. The same BGP session, but you got different routing policy for different address families. Okay, so BGP includes an AFI and an FI. I'm going to call it AFI and SAFI with every route advertisement. Every route advertisement, you got an AFI and SFI with every route advertisement to differentiate between the AFI and the SAFI or AFI and SAFI databases. Okay, your BGP is including an AFI and SAFI with every route advertisement to differentiate between the AFI and the SAFI databases. Now, just be warned here, these facts might shock you. There's two facts I want to drop you now. So number one is that unlike IGP protocol, the BGP does not use hello packets to discover neighbors. Oh yes, that's true. I'm not making this up. This is true. Now the other thing is, if this shocked you, wait till you find out about this. Number two is, believe it or not, but BGP neighbors cannot discover each other dynamically like OSPF or ERGP. Okay, it's not, it's not discovering neighbors dynamically. Okay, this shocked me, but you must keep in mind that BGP was designed as an inter-autonomous routing, inter-autonomous routing protocol, so implying that neighbor adjacencies should not change frequently and are coordinated. So now I want to talk about IBGP and eBGP. So IBGP uses administrative distance. Now, administrative distance is basically like a trust metric value. Okay, it's how reliable that route is. The lower, the better. Okay. Now, an IGP route, BGP route will have an AD of 200. Okay, which is quite high on the spectrum. Okay, a higher meaning a worse. So IBGP is used for sessions established within an IGP router that are in the same AS or in the same BGP same BGP confederation. Sorry, that should say confederation. Okay, but eBGP uses AD20. Okay, so eBGP is for sessions established with a BGP router that are in different autonomous systems. Okay, so eBGP, look in more detail. These behaviors are different on eBGP sessions compared to IBGP sessions. So time to live, okay, for example, okay, on eBGP packet is set to 1 by default, while for IBGP is 255. So important to remember that. I'll take note of that. Our eBGP package is set to 1 by default, while for IBGP it's 255. eBGP packets drop in transit. Okay, they drop in transit if sorry, just a second. So eBGP packets drop in transit if multi-hop BGP session is established. Okay. Apologies for this. Just a second. Just trying to. Okay. So eBGP packets they drop in transit if a multi-hop BGP session is attempted. So something that I want to know, important to know that. All right. The advertising router modifies the BGP next hop address to the IP address sourcing the BGP connections. The advertising router modifies the BGP next hop address to the IP address sourcing the BGP connection. Okay, the advertising router prepends its AS to the existing AS path attribute, and the receiving router verifies that the AS path attribute does not contain an ASN that matches the local ASN. Otherwise, BGP freaks out and discards the route, like I said before. Okay, so eBGP package drop in transit for multi-hop BGP session is attempted. The advertising router modifies the BGP next hop address. It'll modify that BGP next hop address to the IP address that's sourcing the BGP connection. The advertising router is going to modify the BGP next hop address to the IP address that's sourcing the BGP connection. The advertising router prepends its AS to the existing AS path attribute. Now, like I said, the AS path attribute, okay, it needs to be verified by the receiving router to ensure that it doesn't contain an ASN that matches the local ASN, otherwise BGP is going to freak out and discard it, that prefix. Now, you might be wondering to yourself, why do we use IBGP inside an AS? Can't we just use an IBGP? Well, the answer is no, no, and no. Okay. Okay. The reason is because the IPv4 Internet Router Table contains over a million prefixes. Yes, seriously. And IBGPs are not designed for that scale. BGP stores a huge amount of information about its prefixes with attributes. Now, take for example the AS path. Now, you distribute the prefixes into an IBGP. Okay. If you redistribute prefixes into an IBGP, that information is going to be lost. Now, guys, let's go into BGP messages. So there's 4 types you need to know about: open, update, notification, and keep alive. Okay. Now, this is just an acronym that I use to memorize, just to help me remember them. Only you now know. Open, update, notification, and keep alive. Okay, that's something that works for you, or maybe doesn't, but there's something that works for me. So I just wanted to share that. So open, basically, what that's doing is setting up and is creating the BGP adjacency. Update okay, that's advertising, updating, or moving routes. Notification indicates an error condition to a BGP. Okay, indicates an error condition. Okay, to a BGP neighbor notification, and the keep alive. Okay, ensures that the BGP neighbors are still alive. Okay, you could think about like the heartbeat checker message. Okay, so open sets up, creates the BGP agency, update, advertise, updates, or removes routes. Notifications, they indicate an error condition to a BGP neighbor, and the keep alive is meaning is the heartbeat checker message. I think of it ensures the BGP neighbor is still alive. So open up messages firstly. Okay, used to create that BGP adjacency. Both sides negotiate session capabilities before BGP peering is established. Now the open message contains various parameters. Okay, such as the BGP version number, yeah, the ASN of the originating router, the hold time, the BGP identifier, the local BGP router ID, similar to OSPF, okay, the router ID in the BGP and the OSPF router ID. Now, all the optional parameters also, but yeah, the open messages is used to create a BGP adjacency. Okay, these session capabilities that we have, they need to be negotiated before that BGP peering is going to be established. And the open message contains various parameters that include the BGP version number, ASN of the originator router, hold time, the BGP identifier, other optional parameters. Now, the hold time field, okay, so this field in the open message sets the proceed value for the hold time in seconds for each BGP neighbor. The hold time in conjunction with keep alive messages is a heartbeat mechanism, okay, from BGP neighbors to ensure that the neighbor is healthy and active. Now, when establishing a BGP session, the routers use the smaller hold time value contained in the router's open messages. The hold time value must be at least 3 seconds or set to 0 to disable keep alive messages. For example, Cisco routers, they have a default hold time of 180 seconds. The BGP identifier field is a 32-bit unique number that identifies the BGP routers in the advertised prefixes. Okay, the same amount of bits as an IP address. Okay, or an OSPF router ID. The router ID can be used as a loop prevention mechanism for routers advertised within an autonomous system. Now, the router ID can be used as a loop prevention mechanism for routers advertised within an autonomous system. Okay, the RAID can be manually or dynamically set for BGP, but remember this okay, but remember this non-zero value must be set in order for routers to become neighbors. Okay, okay, so the router ID that can be set manually, or it can be set dynamically for BGP. Okay, just like an OSPF, you can have it dynamically or manually set, but the thing is that okay, that the but remember that, I'm sorry, not this, a non-zero value must be set in order for routers to become neighbors. A non-zero value must be set, okay, in order for routers to become neighbors. Now, okay, how's the BGP identifier configured? Like I said, it is similar to SPF. So basically, you manually configure it with the BGP router ID command, okay, or you can use the highest IP address of the loopback interface or the highest IP address of the physical interface. This is the election process, okay. So firstly, if you manually configure it, that's what's going to take precedence. Okay, if you've not done that, then the highest IP address of the physical loopback interface, otherwise the highest IP address of the physical interface will be chosen. Now, remember, if the BGP route ID changes, all the sessions are reset and they need to be reestablished. Update messages, okay, when BGP routers have become BGP neighbors, they can start exchanging information. The update messages advertise any feasible routes, remove previously okay they will remove previously advertised routes, or they can do both. An update message includes the advertised prefixes in the NLRI and other associated BGP path attributes. Now, prefixes that need to be withdrawn are advertised in the withdrawn routes field of the update message. An update message can act as a keep alive to reduce traffic that isn't needed. Now, what's very important is that if the hold time reaches 0, the BGP session is taken down, routes from that neighbor are removed, and an update message is sent to all the BGP neighbors to withdraw the advertised prefixes. Okay. So if the hold time reaches 0, the BGP session is taken down. Okay. And the routes from the neighbor are going to be removed. An update message is going to be sent to all the BGP neighbors to withdraw the affected prefixes. Notification messages, like I said, is sent if errors are detected in the BGP session. Okay. So if so when a notification message is sent, the BGP neighbor adjacency will be terminated, and the BGP connection is going to be closed. Okay, notification messages are sent. Same slide there. So example of events that trigger notification messages are the hold time expiring, neighbor capabilities hanging, or a BGP session. Okay, that's being requested. Yeah, these cause BGP and connections to close. And keep alive messages. These exchange every 1/3 of the hold time agreed between two BGP routers. Now, as I mentioned earlier, Cisco routers have a default hold time of 180 seconds. So the default keep alive interval is going to be 60 seconds. That's 1/3. Okay, if the hold time is set to 0, no keep alive messages are going to be sent between the BGP neighbors. Now, the final section, part 1, we're going to be looking at BGP neighbor states. So, 6 states that you need to know about. Now, one way I think of them is a game of snakes and ladders, moving between these neighbor states, because it's a bit like a board game in the sense that you're moving from different states. If certain things happen, you can go back a step. It's like you go back to square one, or you could not necessarily go back to square one, but you go back a square. And if certain things happen, you move up, and you move up from idle to connect to active to open, send to open, confirm to establish. So 6 states. I can always out organize everybody. It's just an acronym that I use to help me remember the different ones and remember the order that they come in. But like I said, this analogy of snakes and ladders, I think for me, helps me remember the different states and how different actions lead to moving up the different states, or just certain actions can happen, you go down. And I'll talk about that more. So the idle state, that's the first stage of this. And this, by the way, is called the finite state machine, 6 finite state machine, the FSM, the BGP finite state machine. Now, BGP detects a start event firstly, and it tries to initiate a TCP session to the peer. The start event occurs when someone configures a new BGP event, or when that established BGP peering is reset. Okay, so when someone is going to be configuring a new BGP event, or you got an established BGP peering is going to be reset. Now, BGP also listens for a new connection from the BGP router. Now, if an error causes BGP to go back to the idle state for the second time, the connection retry timer is set to 60 seconds. That needs to decrement to 0 before that connection be initiated again. Further failures to leave the idle state result in the connection retry timer doubling in length from the previous time. Okay, so this is the first state. BGP is going to detect a start event, try to initiate TCP connection to the peer. Okay, we're trying to create that connection. The start event is occurring when someone's going to configure that BGP event, or a BGP peering is going to be reset. Yeah, that's now. Okay, so BGP is listening to a new connection from the BGP router. Okay, an error causes BGP to go back to the idle state for the second. If an error causes BGP to go back to the idle state for the second time, the connection retry timer is going to be set to 60 seconds. Once that decrements to 0, connection can be initiated again. Okay, so you got this timer here to stop which stops connections from us trying to create a new connection, create a new connection, create a new connection, connect a new connection. Okay, you got the connect retry timer. Once that decrements to 0, we can have a new connection being attempted. Now, if we have further failures, that time is going to double. Okay,